Hi there, welcome back to the channel. In the first part of the series, we talked about the introduction and very basic elements of neural networks. This is the second part of the beginner's neural network series. Today, we will look at how neural networks learn to perform tasks that require intelligence, and we will also discuss the activation functions. So, let's dive in. Assume we have a neural network, or you can say a deep learning model that can recognize handwritten digits. So, if an image of handwritten digit is fed to the network, then it can recognize what the number is and generate an output showing the number. When a model takes input and recognizes or predicts or performs any kind of task from the input, then it is called inference. But before a model can perform inference with good accuracy, it needs to be trained. In other words, it has to learn before it can infer. The learning process of a model or a neural network is called training. To train a model, we need a large amount of data. For example, to train our handwritten digit recognizer, we can use MNIST dataset, which contains 60,000 images of handwritten digits for training. The model uses these images to learn the features which will be useful for recognition. Now, after the training, we need to test or evaluate the performance of the model. The performance can be measured by how many images it got correct. In other words, we measure the accuracy of the model. There are different evaluation methods for different tasks. We will explore those as we advance through our series. A separate portion of the dataset is kept for evaluation, which is not used for training. In the MNIST dataset, 10,000 images are kept for this purpose. Now let's look at what happens during training. Basically, there are two steps or phases in learning. First one is called forward pass and other one is called backward pass. In the forward pass, the input values are passed through the network and output is produced. In our example, the pixel values of an image are passed to the network where each neuron performs its operation and passes to the next layer until the last layer where a single value is predicted. The first time the weights are initialized randomly, so the output will also be random. Now there is something called loss function which calculates the gap or distance or difference between the predicted value and the actual label of the image. Depending on the task, there are various loss functions which we will discuss later. Now the loss value is propagated backwards throughout the network. This is called backward pass or backpropagation. During this phase, the weights of the neural networks are adjusted so that the loss is minimized. There are different algorithms that are used to change the attributes of weights. They are called optimizers. This is how a model learns. In the last video, I told that learning happens by changing the weights. Well, learning actually is finding the weights that will minimize the loss and maximize the accuracy. One forward and backward pass makes an iteration. It requires thousands of iterations to train a model. Now let's see what operations are performed during the forward pass. Addition and multiplication are the basic operations that are performed. In the first part, we saw inputs are multiplied with corresponding weights and added together. Additionally, a bias may be added. Now, aside from bias, let's take the input vector and weight vector separately. Now, if we transpose the input vector and multiply it with the weight vector, then we get the same result. Consider one more example. Here we got two inputs and three outputs. So for each neuron in the hidden layer, there will be two weights. For the first neuron, the weights are W11 and W12, which represents the weight of the first neuron from two inputs. The weights of the second neuron are W21 and W22, and W31 and W32 are the weights of the third neuron. Three neurons perform same operation individually. Now, like the previous example, if we take input vector and weight matrix, transpose the input vector and perform matrix multiplication, it gives the same result. Now let's add the bias. So take any number of input and any number of neurons. The operation of forward pass is this simple matrix multiplication. As you add more hidden layers, the neural network performs the same operation in chain. Now, matrix multiplication is a linear operation, so these neural networks can learn relations effectively from the data which are linear. But most of the time, real world data are non-linear. So, to make our neural network suitable to real world data, we need to introduce non-linearity. And the way we do it is by using an activation function, specifically non-linear activation function. Activation functions decide whether a neuron should be activated or not. They are differentiable operators to transform input signals into outputs. They need to be differentiable for backpropagation, which we will see in a later video. Activation functions are fundamental to deep learning. Let's briefly look at some common activation functions. First one is rectified linear unit, in short ReLU. It is a very simple function. It is defined as given an element, the output is maximum of 0 or the element. ReLU is the most popular activation function. It retains only positive elements and discards all negative elements by setting the corresponding activations to 0. It looks like this in graphical representation. ReLU is mostly used in hidden layers. The next activation function is called sigmoid function. The sigmoid function transforms the input, which range from negative infinity to infinity, and produce output of range 0 to 1. It is also called squashing function because of this behavior. Sigmoids are widely used as activation function on the output units when we want to interpret the outputs as probabilities for binary classification problems. The graphical representation of the sigmoid looks like this. Another activation function is the hyperbolic tangent function or tanh function. It also squashes input of range negative infinity to infinity to the output of range negative 1 to 1. Hyperbolic tangent function becomes linear as input approaches to 0. In the next video, we will see the loss function and how neural networks learn through backpropagation. If you enjoyed the video and learned something from it, please like it and consider subscribing to the channel, and of course share with your friends. Thank you very much for watching.